Welcome to week 7, question 1, and it says find all local extrema. So let's understand what extrema are. Extrema are extremes of a function. So where a function reaches its maximum points and where a function reaches its minimum points. And if I simply draw a function here for a demonstration, you could see that here that function is at an extreme high point or maximum, and here the function is at an extreme minimum point. And what we have to understand about identifying where those points are is they are points where the function changes from a slope that's going positive to a change in slope through that point and through a change that's negative. And here, for example, when the slope is negative and changes to a positive, and it has to again go through a place where the slope equals 0 at that maximum or minimum point. Now, if we recall, the derivative is defined as the rate of change or the slope of a function at a point, then that's where that slope is 0. If we find the derivative of a function and we set that equal to 0, we're going to be able to find at what point those extrema or maximum and minimum points are. Okay, so let's see how we go ahead. The question reads, the function f at x equals, we've got our function there, approximates the number of construction workers employed in a certain state where x equals 0 corresponds to the year 2000. Okay, so we've got some important information. It says find and interpret all local extrema. So the term local means that you're looking for maximum and minimum points that occur over the entire length of the function. Later we're going to look at absolute extrema, which are going to be those maximum and minimum points within a certain range. Okay? So here we're looking for all possible extrema over the entire function. So again, we need to find the derivative of the given function, and then we're going to set that derivative equal to 0, solve for x, and we're going to get the x value at that point where the function has a maximum or minimum. Okay, so if we look at the function we're given here, first thing we need to do is identify the function, get to know what we're working with. And we can see that it's a fairly basic function. We've got sums and differences, we've got power terms, and we have a constant. So we have 4 terms, and let's have a look at how we would approach this. So for the first term, we would use the power rule. Let me just remind you what that looks like. Any variable to the power n, the derivative will be nx to the n minus 1. Okay, let's put that aside so we can use that to help us. So here in the first term, we would be multiplying negative 0.547 by 3. And there we would have negative 1.641 x squared is the first term. Addition sign, we have 16.072 x squared, so it's going to be 2 times 16.072, which gives us 32.144, and it's x, so 2 minus 1 is x to the 1. And the third term, negative 102.955x, the derivative of that term is just that value, and the derivative of 658.046, it's a constant, so it's going to be 0. So here's the rate of change of construction workers employed in this certain state. Okay, that's what we've got here, rate of change. So the next step now is going to be to find those critical points, those points where the slope is 0, where that slope is at a maximum or minimum point. So we can look at the function now and say, well, we've got a quadratic. We have an x squared term. So we have a quadratic function. And in order to find the roots or the values of x, we're going to need the quadratic formula. It's not going to be easy to factor this function. So let's go to the next page and we'll apply the quadratic formula. So here we have the derivative rewritten in front of us, and again we're going to be looking at the quadratic formula. And remember, we need values of a, b, and c. A, b, and c. Don't forget, we're taking the signs as well with us. So quadratic formula, x equals negative b plus or minus square root of b squared minus 4ac, and all of that over 2a. So to fill in our values, we have x is equal to negative 32.144 plus or minus the square root of 32.144 squared minus 4 times negative 1.644 times negative 102.955, and all of that is over 2 times negative 1.644. This would be a good time to remind you to use your order of operations. Remember, BEDMAS is going to be our little keyword, right? Where we've got brackets, exponents, division, multiplication, followed by addition and subtraction. So we've got some values in here we want to work on first. We want to square that, our exponent squared, before we do any subtraction. And then we're going to have two values. This plus or minus means that we're going to have two values for x. And when we work out all of this, we're going to have x is either equal to 15.55 or x is equal to 4.03. Okay, so what exactly does that mean? We have some numbers. We seem to have arrived at them through some legitimate math process, but what do they mean? Okay, so it means that we have x equals 0 corresponds to 2000. So we're looking at when x is 15.55, that corresponds to the year 2015 and a little over half of that, 0.55. Or here we have 2004. So what those numbers mean is that there was an extreme value of construction workers, either a maximum or a minimum number in those 2 years, 2015 and 2004. So how are we going to find out which one is maximum and which one is a minimum? You'll recall in the first slide I said that when we're looking for extrema, we're looking at places where the slope is 0. So we were able to determine the x values when the slope is 0. But how do we know if it's a maximum or minimum? So here we would have a maximum point, right? It's the highest point in the curve. And here we would have a minimum point, for example. This is just a sketch, not of this function. So how do we decide if those values we had of x, which is 15.55, and 4.03, represented maximum or minimum points? Okay, so if we look at the slope, the landscape of this slope before this maximum point here, we see that the slope here is positive until it reaches that place where it is 0, and then on the other side of that point it is negative, and that represents a maximum point. Conversely, when we're looking at this minimum point, we see that the slope here is negative until it goes through that extrema where it's 0, and then the slope on the other side of that point is positive. So what you need to do is use test points on either side of these points that you've determined are the extrema points. So test points as in, why don't we use f prime at 0? That's an easy one. And solve. Let's use f prime at 10, because that's a point which sits between 15 and 4. Let's pick a point f prime at 20, because that sits on the other side of 15.55. And then we will know what the changing in slope is, whether it's positive, negative, or negative to positive. Okay, so these test points are going to be used in the derivative that we found. And so if we put them in the derivative, we find that f prime at 0 is negative 102.55. Okay. We find that f prime at 10 is 54.385. We find that f prime at 20 is negative 116.475. Okay, so you can see that the values of these test points are changing. So here we have negative slope, a positive slope, and a negative slope. Our points at the extrema sitting in the middle. So we've got in here, we've got x is 4.03, and sitting in between here, we have x is equal to 15.55. So if we consider that from 0 to 4.03 to 10, our function goes from a negative slope through to 0 and up to a positive slope, you can see that we're looking at a minimum. Okay? So that describes a minimum. And then we look at 15.55. It sits between f prime at 10, which has a positive slope, f prime at 20, which has a negative slope. So we're actually going from a positive slope to a negative slope, which defines the behavior of a maximum. Okay, so there we have it. The next part of the question says to evaluate the number of construction workers employed at that maximum and minimum point. So let's see how we would do that. So to determine what the maximum number of construction workers were employed and the minimum number, we're going to substitute back our values at the extrema back into the original function. Okay, so you would be solving for f at 15.55, and you would be solving for f at 4.03, and let's see if it bears it out. We've got 886.61 and 468.36. So we said by using our test points, we determined that there was a maximum at 15.55, so 2015, there's a max. And in the year 2004, there was a min. And if we look at our values, then yeah, we can see that 468.36 is less than 886.61. Perfect.